Welcome to chapter 14 on the part that deals with shifters. Okay, so you may have encountered shifting operations or shifting instructions in your favorite programming languages. For example, in C and Python, if you want to shift the string A by 5 positions to the left, you write this command, and this would be 5 positions to the right. What exactly do these shifts signify and how do they work? We will talk about this. How are these shifts executed in a microprocessor? We will also talk about that. And we will also address the following point. Is shifting actually implemented by a combinational circuit? Because we think of combinational circuits as devices that compute functions. And shifting is not really a function because it just moves bits around. Okay, it doesn't compute new bits. Okay, so we'll talk about that too. I want to give you some motivation for cyclic shifts. So suppose I have a string of 12 bits or 12 numbers, not necessarily bits, they could be also numbers, and I position the numbers along a clock. So in the first position I have a 5, then I have a 3, 1, 11, 9, 7, 2, and so on. Okay. Now what I do is I view this clock as a dial or a wheel, and I rotate it by 3 positions in the clockwise direction, right? So I do a rotation clockwise. So now the 12 moves 3 positions, so it will be at 3 o'clock. So here you can see the 12 at 3 o'clock. The 5, which starts at 1 o'clock, moves by 3 hours to 4 o'clock. So now the 5 is over here. So you can read the string that used to be 12, 5, 3, and so on. The 12 is here, the 5 is here, the 3 is here, and so on. And now in position 1, for example, you see 8. And 8 used to be in position 10. So when you move 3 positions from 10, you go 1, 2, 3, you reach 1 o'clock. So this is why the 8 is in 1 o'clock. Okay, so this is called a cyclic shift of strings of length 12 in clockwise orientation. Okay, recall we denote the remainder when you divide A by B by A mod B or by mod A comma B. Okay. We say that the string B, which is a string of n bits, is a cyclic left shift by I positions of the string A if for every j, bj contains the bit that is in A in position mod of j minus I, comma n. So what happens here is when I do this subtraction j minus I, if it's positive, then there's no problem, I don't need the mod. The problem is that this difference, j minus I, might be negative. And if it's negative, what does A in a negative position mean? Well, then we have to take the remainder or simply add n to the difference in order to figure out the right location in A. Let's see an example. If A is the string 0, 0, 1, 0, and this 0 is the least significant bit, and this 0 is the most significant bit. And now we want to perform a cyclic left shift by 1 position to the left. Then you take A and you move all the bits of A to the left. So this 0 moves 1 position to the left. This 1 moves 1 position to the left. This 0 moves 1 position to the left, and this 0 is lost. And in this position you will get a new, it's not lost, it is moved to the first position. Okay, so when you do this cyclic rotation, you started with, let's say, 0, 1, 0, 0, right? And now you moved everything, so by 1 position. So now you will have this 0 will be over here, the 1 will move to here, this 0 will move to here, and this 0 will move to here. Yeah? That's the outcome. And therefore the result This is position 0, this is position 1, this is position 2, and this is position 3. This is position 0, 1, 2, and 3. So the outcome of rotating the string 0, 1, 0, 0 by one position to the left is the string 0, 0, 1, 0. And this is what you see over here. Okay? Now if I were to shift A by 3 positions to the left, and what happens to the 1? It goes 1 position, 2 positions, and then it goes back to the beginning. And that's where you see the 1 over here. Okay? That completes the example. Let's define what a barrel shifter is. A barrel shifter with parameter n is a combinational circuit with the following inputs. It has an n-bit string x as an input and a shift amount SA, which is k bits long, where k equals log of n base 2. Y, it has the same length as x does, and the functionality is that y is a cyclic left shift of x by SA positions. You look at SA and you think of SA as encoding a number in binary representation, and this is the number which specifies the number of positions by which you perform the shift. So formally speaking, yj should equal x in position mod of j minus the shift amount, comma n. We refer to x as the data input. We refer to SA as the shift amount input. And to simplify the discussion, we will assume that n is a power of 2, and therefore you don't need this ceiling and life is easier. Okay, how do we implement a barrel shifter? We break the task of designing a barrel shifter into smaller subtasks of shifting by powers of 2. And we define this subtask formally as follows. A cyclic left shift n, 2 to the I is a combinational circuit that implements a cyclic shift by 0 or 2 to the I positions. Okay? And the decision whether you shift by 0 or 2 to the I positions depends on an extra input called the select input. So CLS-NI is a combinational circuit defined as follows. Has an input x and s, which is a single bit. This is your select input. The output y has the same length as x, which has n bits. And the functionality is that yj is going to be equal to x in position mod of j minus s times I, comma n. What does this mean? It means that yj equals xj if s is 0, in this case no shift takes place, otherwise it equals x in position mod of j minus I, comma n, if s is 1. So as you can see, it either doesn't perform a shift at all or it performs a shift by I positions to the left, a cyclic shift. How do we implement this CLS n, I circuit? It's very simple. Since yj is one of 2 bits, all you need to do is feed these 2 bits to a mux gate, and the mux gate selects between xj or x of mod of j minus I, comma n, depending on the value of the select bit. Okay, so we have the select bit feeding the muxes, and we have the outputs of the muxes, and each mux has 2 inputs. One is the corresponding bit of x, and the second one is the shifted value of x. So this is a CLS for 2. Okay, so if shifting takes place to the left, then the 0 bit goes to the second position, the first bit goes to the third position, the second bit goes to the 0 position, and the third bit goes to the position number 1. Okay, so this is a circuit. Another way of thinking about it, a CLS-NI, is you have a row of muxes fed by x and by the cyclic left shift of x by I positions, and the mux simply selects between these 2 values to give you the output y. The point is that I didn't want to have the extra input, which is the shifted input of x, and therefore I had to draw these long lines. And in fact, these long lines are interesting because in practice, when you implement a shifter, you will need these long lines, and these long lines consume space, they consume area in your VLSI chip, and they have resistance and capacitance and whatnot, so they have some unpleasant effects on the performance of the circuit. Good. If we go back to the implementation of the barrel shifter, the design of the barrel shifter is based on cascading CLS circuits. So we will have K levels, one for every bit of the shift amount. The first level is fed by SA0, the second one by SN1, until the last one, which is fed by SAK-1. You take X, and then you either shift it by one position or not, depending on the value of SA0. The result is then shifted by two positions or not, depending on the value of SA1, and so on and so forth, until you get Y. And this is your barrel shifter of length N. I want to recall some properties of the modulo function. Mod of x comma n equals the modulo of x plus qn comma n. Namely, if you're taking the remainder when you divide by n, then it doesn't matter if you add multiples of n to the number you're dividing. And the second observation is if I take a and I look at its remainder when I divide it by n, let us denote it by alpha. And the same thing with b, we divide by n, we take the remainder, this will be beta. And now we look at the difference, a minus b and alpha minus b, beta, and we look at their remainder when you divide them by n, then these two remainders will be equal to each other, and we already proved this in chapter 5 on binary representation. You can see slide number 5. Good. So now we claim that the barrel shifter that we just depicted, the one with the cascade of the CLS circuits, is a correct implementation of a barrel shifter, and the proof is by induction on I. We claim that the output of the ith stage of the cascade is indeed the cyclic shift of x by this many positions. Okay, so let's prove this statement. The induction is on I, so let's look at the induction basis. When I equals 0, what is this CLS n comma 2 to the 0? Well, it either shifts by one position or by 0 positions, depending on SA0, and this is exactly the statement of the induction basis. The induction hypothesis tells us that if I look at the first I, this would be I plus 1 stages of the cyclic shifter, the value of Y, which we see over here, is the shifting of X by this many positions. Now we go to the next step, and in the next step we apply a CLS n comma 2 to the power of I plus 1, which is controlled by SA I plus 1 and outputs Z. Now Z is a shift bar of Y by how many positions? It is 2 to the I plus 1 times SA in position I plus 1 positions. Why? Because if this bit is 0, you don't perform any shifting. And if this bit is 1, then you perform a shift by 2 to the power of I plus 1. Okay? Now, Y itself, by the induction hypothesis, is a shifting of X by this many positions. So I know that Z is a shifting of X by this many positions, plus the extra shift which you have between Y and Z. Now, this shift amount is exactly the number represented by SA in positions I plus 1 to 0 in binary representation, and that completes the induction step. What is the cost and the delay of our circuit? Let's go back and see the implementation. The implementation consists of a cascade of K CLS circuits of width n. Each such CLS has n muxes, so we have here log n stages with n muxes, so the cost is n times log n times the cost of a mux, and the delay is just the sum of the delays of the cascade. Each cascade has a delay of 1 mux, so in total the delay is k times the delay of a mux, or in other words, it is log n times the delay of a mux. Okay, so the cost is n log n. We have a width of n In each stage, the number of stages is log n, and this will be our delay. Good. We may ask about lower bounds. How good is this barrel shifter? Well, consider the output y0 of the barrel shifter, the least significant bit of the output. We claim that the cone of the Boolean function implemented by y0 contains at least n elements. Indeed, xi is in the cone. And why is that? You just set the shift amount to represent the number n minus I, and then you know that y0 simply equals xi. So if you flip xi, you will flip the value of y0, and therefore xi is in the cone. So all the bits of x are in the cone of y0, therefore the cone of y0 contains at least n elements. Therefore, the delay of the barrel shifter is asymptotically optimal because it is logarithmic, and it has to be logarithmic. Okay. One can also show that the cost of the barrel shifter is asymptotically optimal, but that is beyond the scope of this course. Now let's talk about logical shifts, which are somewhat different from cyclic shifts. In a logical shift, if we're, say, talking about a left shift, you can think of it as if I took x and I padded zeros from the right. And now when I perform the shift to the left, so this is a left shift, then the zeros start entering the lower index positions of x, and the higher index positions of x are simply lost. Okay, and this is what is written over here. yi will equal 0 if I is less than the shift amount, and otherwise it is x in position I minus L. Let's see an example. My x is 1, 0, 0, 1, and I want to shift it by 2 positions to the left. This is a logical shift. So the 1 will move by 2 positions, the 0 will move by 2 positions, and so on. So this is the 1 that used to reside in position 0. This is the 0 that used to reside in position 1. And these two zeros were pushed in from the right. Okay? So we always know that if you perform a left shift by L positions, you will have in the result of the shifting on the least significant part, you will have a block of L zeros. Okay? And in fact, if you think about it for a minute, in binary representation, logical shifting to the left by S positions corresponds to multiplying the number by 2 to the S. Yeah, because every time you multiply by, you perform a shift by 1 position, it's like multiplying the number by 2. And there is a problem because you have these bits which fall out. So you should regard it as multiplying by 2 to the S, followed by finding the remainder when you divide the number by 2 to the n, because these are the bits that are lost. Okay, so logical shift is a fast way of performing multiplication by powers of 2 in binary representation. You could also talk about right shifting. In right shifting, this is your string. This is, of course, the least significant bit. This is the the most significant bit. And now you're doing a shift to the right. So you are padding zeros from the left, and they're pushing them inside. And this is what you see over here. yi will equal 0 if I is greater than or equal to n minus L. Otherwise, in position I of string y, you will see x of index I plus L. Let's see an example. I start with x, which is this string, and I want to perform a right shift now by 2 positions. So this is a right shift. This one will go to here. Sorry. This one will go to here, and this 0 will go to here. And you will push in 2 bits from the left. So you will get the string 0, 0 from the left, and then this one will be in this position. You see it here, followed by a 0. Okay? When we apply a logical right shift to x by L positions, we know for sure that you will have on the most significant bits L zeros. In fact, if in binary representation, logical shifting to the right by S positions corresponds to the integer part of the quotient when you divide by 2 to the power of S. Good. Let's introduce the following notation. This will be logical left shift of x by I positions, LLS, and this will be logical right shift of x by I positions, LRS. Okay. Now let's think of a bidirectional logical shifter. It's a combinational circuit. We have a parameter n, which specifies the length of the input x. We have a shift amount, which is log n bits long, and we have an extra bit L. L tells us if we want to go left or not. So if L equals 1, it means it is a left shift, and if L equals 0, it means it's a right shift. And our output Y should satisfy the following. If L is 1, we perform a logical left shift of x by SA positions. If L is 0, we perform a logical right shift of x by SA positions. And now our goal is to design a bidirectional shifter using a left shifter and a right shifter, if you know how to do a right shifter, and then you select the right answer based on L. So that would be one way to design our bidirectional logical shifter. Let's present another way of doing it. Okay, but before we do it, let's see an example. X is the string 0, 0, 1, 0, and now we want to shift by 2 positions, and left L is 1, so we do a shift to the left. That means that this one goes to this location, and therefore you get Y, which equals this fellow. Now, if L is 0, that means you're doing a shift to the right. That means that this one moves 2 positions to the right, that is out of the string, and therefore it's lost, and your string becomes, the output becomes all zeros. Okay, so let's try to implement a bidirectional shifter. We'll break it into stages as we did in the cyclic shifter. We will have a logical bidirectional shifter of n bits by I positions. The input is x, 2 bits of control. One says whether you want to perform a shift at all, and the other one tells you whether the shift is to the left or to the right. And you have the output y, and the output y is simply x if there's no shifting taking place. If a shift is taking place, then the L determines whether it is a shift to the left or whether it is a shift to the right. Okay? Good. So let's try to implement this bidirectional shift by I positions. So this is xj, and if you want to perform no shifting at all, you choose xj because the shift is 0, so you choose this xj. Now, if you want to do a left shift, right, then you need to output in position j of y, you need to output j minus 2 to the power of I. This is, of course, provided that this number is not negative. What do you do if this number is negative? So for that purpose, we define x prime. I didn't write what x prime is, so let me explain what x prime is. X prime, so what you do is you take x, this goes from position 0 to position n minus 1, and now you pad zeros in position -1, -2, and so on, and also in the high positions. You pad zeros, and this is x prime. Good. So now we don't have a problem with modulo or with being above n or whatnot. We know that these are all zeros. Whenever this number is too big or this number is too small, we mean a 0. Okay, good. So this is what you need if you want to do a left shift, and this is the bit you need if you want to do a right shift, and you choose, if you do a shift, you choose from this branch, and you choose the right input according to L. Okay? So now what we want to do is we want to design a bidirectional logical shifter which is based on cascading these LBS circuits for powers of 2. Okay? Okay, let's see another way of implementing a bidirectional shifter. The other way we want to do it is by employing a reduction from right shift to left shift. So let's see how this reduction takes place. Let's look at the reverse function. This is a function that when given a string, it reverses the string. Okay, so the reverse of 0, 1, 1 will be 1, 1, 0. Okay, and a hardware for performing reversal is 0 cost and 0 delay, because all you need to do, if you have the x0, x1, and x2, and you want the output y0, y1, and y2, then all you have to do is connect these things like that, and there's a 0 cost and 0 delay. Good. So now we notice that by using reversals, we can reduce a right shift to a left shift. Namely, if I want to perform a right shift by I positions, I take A, I reverse it, then I do the left shift, then I reverse it, then I get the correct right shift. Okay? So I will leave this as an exercise to you to check that indeed this claim is correct. Now I can have a shifter that either performs a left shift or a right shift. This is a bidirectional shifter. And how does it work? Well, if I want to do a left shift, then I do not reverse the string. If I want to do a right string, I reverse the string. Then I do the left shift, and again, if I wanted to do a left shift, I keep the output of the shifter. Otherwise, I reverse it, and that will be my output. So this is a bidirectional left shifter that does either left or right, always, okay? There's no option here of not performing a shift at all. If you don't want to perform the shift at all, you could add a mux at the end, which selects between X and this output. Okay, finally, I want to talk about arithmetic shifters. Arithmetic shifters are used for shifting binary strings that are represented in a special technique that allows you to represent numbers that are negative, what is called signed integers, and this technique is called 2's complement representation. Now, left shifting is the same in logical shifting and in arithmetic shifting, so we will only discuss right shifting in the context of arithmetic shifters, and this is in fact a division by powers of 2 with respect to 2's complement representation, which we haven't defined yet. Good, so the binary string y is an arithmetic right shift by L positions of the binary string x if the following holds. And what we do here, in fact, this is standard, this part is standard, and this part is a little bit strange. So let me elaborate on what this part says. So you can view it as if I took x, and this is the LSB, and this is the MSB, and I padded it by the most significant bit of x. So this would be xn minus 1, xn minus 1. So I'm padding copies of xn minus 1 in this fashion, and therefore when I'm performing a shift to the right, then shift to the right will push in bits which are copies of the most significant bit of x, and this is what you see over here. Okay, so the high order bits of the shifted output will be copies of the most significant bit of x. So for example, if I start with a string x, which is 0, 1, 0, 1, and I want to perform an arithmetic shift by one position to the right, so this is like shifting to the left by -1 positions, so this is shifting to the right by one position, then this 1 will go over here, this one falls out, and this is why I see this string as the output. If I wanted to do a shift by 2 positions of x, then this one would go to this position and this one would fall out, and this is why I see these 2 bits. Where do these 2 ones come from? Well, these 2 ones, recall, are copies of the most significant bit of x. The most significant bit of x is 1, and therefore when I did a shift, I get here a 1. Okay? The most significant bit here was 0, so when I did a shift by one position, this is the 0 I see over here. The most significant bit here is 1, and therefore I see here 2 ones in the beginning. Okay, when we perform an arithmetic shift to the right, or you could say to the left by a negative amount, that's the same thing, then you will have L copies of the most significant bit, followed by the rest of x. Okay, we denote by ARS x comma I the arithmetic shift of x by I positions. We'll leave it as an exercise to see how this thing is implemented. Okay, and then we would like to implement an arithmetic shifter. That's a combinational circuit defined as follows. It has an input x, n bits long, shift amount k bits long, output y, which is the sign extended arithmetic right shift of x. This is the shifting we talked about by SA positions. This is the definition. We saw an example, and we'll leave it as an exercise to design an arithmetic right shifter, which is obtained by cascading ARS circuits. Thank you very much.